All right. So, hello and welcome back. I've just discovered how to use the laser pointer on here, so I'll actually be able to point things out that I thought I was pointing out in the surface mine presentation. But anywho, I found it, and here we go. So, this is going to be an overview of underground mining techniques for MIET 392. Um, This is going to be a little bit longer, so buckle yourselves in because there's about 82 different types of underground mining. Not really, but there is more to cover than there is with the different types of surface mining. So with that, let's get into it. So there are three classes of underground mining. Those are unsupported methods, supported methods, and caving methods. Just the three types. But each one has multiple subtypes, as we're about to find out. So, unsupported methods. Those include room and pillar mining, which typically is tabular seams, flat or moderately dipping, and it allows for a very flexible mining geometry. Something that you can't necessarily get out of a longwall mine. Next, we have sublevel and shrinkage stoping. These are for steeply dipping or vertical ore bodies with a strong host rock. Okay, so basically, think of this as you are creating an opening underground. You don't backfill it, and the rock is strong enough that it doesn't cave. So I know we're putting in patterns of roof support in most of our rim and pillar mines. And some of these sublevel and shrinkage stoping operations do that as well. So you're putting in, this like support, but you're not really. You're just holding up that immediate roof or rib, and the rest of it is supporting itself. Okay, so this is the unsupported methods. You don't backfill it, rock doesn't cave. Okay, so first up, rim and pillar mines, which my background is mostly rim and pillar. I've done research in longwall mines as well, but my area of expertise is a deep cover, cold pillar recovery. So that's what I do. But I chose this picture because here you have a nice limestone mine, right? And I chose it because look how massive these spans are in these underground limestone mines, and it makes a very nice figure, so that I can point out exactly what a room is and exactly what a pillar is. So you mine out these openings, you leave pillars to support the overlying overburden. That's simply a room and pillar mine. The last room and pillar mine I was in was a coal mine that I was doing some research in central West Virginia. This is published research. This was at the Maple Eagle mine. So you can see here, we've got rim and pillar, and they're mining these mines. A lot of times now, you're basically mining, what was left behind from other mines, right? So a lot of times they're, sort of cut off for mining is this parting thickness, right? And there are places where it's 4 feet thick, and so what I was trying to do was I was trying to determine how much that rock parting impacted the strength of the pillars on this section. And I successfully accomplished that. So we took two separate measurements from these half leaf blocks over here, right? So I actually got to, from pressure data within the pillars, I got to watch these pillars fail. The pressure would increase just as you would expect as mining progressed, and then eventually you get to the peak stress, and then of course You get to the strain softening portion of the pillar response, where the stress decreases, but the strain is still increasing. You're still having movement, and then you got to a residual load. And I successfully made 3 out of 4 a BPC measurements match up bang on. The fourth was just a little bit off, and as far as I'm concerned, this ended up being a home run. And as far as I'm aware, which I should be aware of everything, this is the first time that was ever measured, right? And it turned out that it was accurate, that it did increase the strength of the pillar, and that it was approximately 50% of that rock thickness, that you could reduce the height of the pillar for your design. We'll get into a whole lot more detail about pillar design later on, but I thought I'd throw this in here as a nice example of a room and pillar mine where retreat mining was practiced here. There's also some multiple seam interactions in this area. You'll see these stress values don't really look like contour lines, and that's because not only do you have the overburden stress, there's also multiple seam interactions in this second panel, which was also retreat mined mostly successfully. They did end up having a roof fallback here while they were mining, and ended up just kind of abandoning the panel somewhere up in here. But anyways, mostly successful. And then, of course, here's where it gets a little bit confusing. So room and pillar mines, especially in coal, end up becoming a caving mining method, right? If you do practice pillar recovery, retreat mining, pulling the pillars, all those things mean the same thing. And in here you have one of my favorite photos of all time that I've ever taken. You've got the miner operator standing there on the left with his arm on the drum, and you're watching the MRSs being pulled back, towards the miner there, so that they can reset and take another lift out of the pillar off of both sides. So this was a full Christmas tree method, yeah. So this is room and pillar, and once again, once you start pillaring, you start caving the top, it kind of changes the mining method, even though you're still using room and pillar techniques in the rest of the mine, right? The mains and all that. So it's a bit of a gray area there. There are also a lot of other commodities that use room and pillar mining. The vast majority of underground mining is this method, right? For all commodities, probably in the neighborhood of 70% or so. So we have trona and potash as well that are typically mined in this. There are also room and pillar gold mines as well that have ore bodies that are conductive to that type of operation. Pretty much anything that's flat or can be mined flat or moderately dipping, you have this. You'll see in this photo some interesting, you'll see that the ribs are curved here. The development in trona is mostly tunnel boring machines, because the material's so hard, and so they'll actually take two lifts to mine this full width. Sometimes they do lift and a half if their ground conditions warranted. But this is a standard room and pillar mine. Also, we have salt. Salt's very commonly mined with techniques like this, and salt's pretty strong material, and you can see how almost beautifully these 90s on these corners are. I mean, they're just perfectly straight. The salt's strong. You have relatively large openings. It's mined really similarly to coal and limestone in this case, but you're using very large equipment, right? You've got the big 4160 joy miners, and because you're mining really high heights, and you can also do multiple level because typically salt is in domes, so you have multiple levels of this. You can also get multiple levels of trona. That's kind of a new territory for them, actually. Trona is only mined in this country in one place in Wyoming out near Rock Springs. It's a pretty vast reserve, and there's several levels out there that can be mined. They're primarily mining in like 2 of the levels, I think. But their plans are to basically move down to another level and start mining again. So they're going to eventually have multiple level, multiple seam, the potential for interactions as well. Salt and Trona as well exhibit creep behavior, because Trona is a form of salt. It's not sodium chloride, but it is an evaporite. They do experience creep, in which this material moves very slowly, but it moves forever. Okay, it will not stop. There are sort of dynamic or stretchable bolts they've even tried in some of these conditions, and it really just boils down to it eventually will close up on it just creeps forever. So you basically had to go back in and rebolt, sometimes remine out places that have been standing for a long time. Now, sublevel or open stoping. Now, we're getting into terms that I haven't studied in a while, but fortunately, there are some excellent diagrams and YouTube videos out there by Alice Kopko for several of these hard rock mining methods, some of which are more popular than others. In this case, you've got sublevels that you're using to access the ore reserve, right? And then it's blasted down, okay, and then it's loaded out from the bottom. Now, with that, because you're blasting more and more ore over top of it, you do have to load out some along the way because of the bulking factor. But eventually, the entire vertical ore body is extracted through the draw point, and then down like that. You can actually mine this in overhand or underhand methods. So you can actually mine top down or bottom up. I mean, typically from a production perspective, you'd want to mine, top down, access your ore as fast as you could. However, there are reasons why you would want to do it the other way. Maybe some of the higher grade ore that you need is further down in the ore body, right, or something like that. You can be more selective with this method, okay, in how you want to, which parts of the ore you want to mine first. And then because it's not backfilled, right, remember, this is left open and it stays open. Okay. And then we have what's called shrinkage stoping. This is a little bit different, okay? In this case, what happens is you've got your axis drifts here, draw points and chutes in here, okay? Once again, a relatively thin, vertical or steeply dipping ore deposit. It has to be dipping enough to where the ore can flow downhill, right? So typically over 50 degrees, the ore's got to be able to flow. But what they do here, you shoot down the ore, okay, and it's left in place, right? You leave it in place, and then you come up, you draw off some, right? And then you'll bring in drills over on top of the broken ore, and you'll drill up in and shoot down another layer. Do it all over again. And you draw out all the ore from the bottom, okay? This is once this ore is all removed, this is left open, and it doesn't cave. Okay, so strong, hanging wall, foot wall, roof and floor, however you want to think about it. Host rock has to be strong. Supported methods. Okay, now we're talking about backfill, right? Or heavy use of timbers. Okay, so we've got cut and fill stoping. That's typically for narrow, regular, steeply dipping. Um, the method is expensive, and it's primarily used in weak host rock, right? So common in the Nevada gold mines, right? So what you're doing is you take out a cut, you take out material, and then you backfill it with whatever. You can use sometimes use waste material. There's also paste you can backfill. There's like a slurry sand backfill. There's a number of options to use, but what it does is allows it supports the rock, right? The rock is not going to support itself. You got to put something in there. Stull stoping, once again, narrow, steeply dipping. It uses timber supports, right? So stalls were basically just large timbers, right? And because this is used in a moderate host rock strength, so not as weak as cut and fill or square sets, you can get by with less support, right? There are also the option to use a more modern method of backfilling with material in areas where the timbers aren't enough. So you can do both methods kind of together with Stull stoping and with square sets as well. So the last one, square set stoping, I think that's probably what most people are familiar with when they think of Western U.S. gold mines, where they would go in, they would mine in, and when they would hit the gold vein, they would start mining down, right, down the vein. And they would mine out these areas and set these series of timbers in cubes, right, because it's a vertical situation. And we'll see some figures of that here as we go along. So cut and fill, right? Here's an example of cut and fill stoping. In this case, it was once an open pit mine, and now they've decided to go underground. So kind of the first thing they do, they think about, where's your access shaft going to be, right? You're also going to need vent shafts. Do you need a ramp? In this case, they have ramps coming from the pit down to these other haulage levels, and then there's actually a second ramp in here to get down to the production levels, right? So what happens is you come in on level one, you've designed this sort of sill pillar, I think that's what they call it, a sill pillar, that is protecting the surface here, and then you start mining out. So you'll mine out in this level, and then backfill it, and then come down and do it all over again, and just repeat it all the way down through here. You can do exploration drilling even further down. See, these are really you couldn't drill these from the surface. So a lot of times they're drilling or just mining drifts, exploration drifts as well, into these lower levels that they're planning on mining soon or in the future. Here's a photo on the right. This is actually a bolt machine, and they're putting in mesh and roof support in here in the form of, I don't know, I can't tell exactly what kind of bolts those are, but they're putting rock bolts in here as well. There's backfill and for where the material has already been taken out on the right side, and they're working their way down. That's about what it looks like. Okay. Stull stoping. So this method looks pretty awesome, if you ask me. It's not widely used anymore, if at all, in this country. I'm not actually sure about that. But what awesome photos. You've got this guy, you've got timbers supporting the entire thing, right? So you've mined out the entire ore body, okay? And you've got these giant horizontal or dipping, depending on the angle, timbers set in here. And those are the stalls, right? These are called stalls, and that's how they mined this. On the right, you can see another a wider example of this. And this is an excellent view. This is more steeply dipping, more vertical. They've actually got ladders here, between levels. So it's neat. But like I said, not widely used anymore. And then finally we have square set stoping. Now this is a very wide angle view of a portion of an ore body that's been extracted using square sets, and you can clearly see these square, and once you make them 3D, cube timber sets that are set in here. Okay, and so this is for use in rock that it's basically so weak that if you mined out more than this volume, it's going to collapse. Okay, so they would mine out a cube and just set these timber frames in there, and they would work their way down the ore body. Also, a more modern technique of this, you can actually also do filling methods in here as well. Okay, in place of the square sets, you can do that too. So, but once again, these are less common mining techniques, at least in this country. Could probably be used in other places in the world, but this is like an example of what you would have seen like out in Colorado or something, or in Nevada, whereas this is an older famous drawing of square set stoping in the mines of Gold Hill, Nevada, from the Comstock lode. And once again, you see miners on various levels, right? Just kind of working their way down and setting up these square sets as they go. Okay. Caving methods. Now this is fun. The number one caving method in the world, at least as far as production, is block caving. These are very large gold, copper, diamond mines, or in the case of the United States, we have a molybdenum mine that's block caving. And there is another block caving, I think it's copper though. I have to double check. The Resolute project out west, it's also going to be block caving. There's also sublevel caving, which is similar to block caving, except you're doing it on sublevels as opposed to all at once. Top slicing, where you would take a slice off the top and then and sort of work your way down like that. It's now obsolete. It's not being used. And then of course we have longwall mines, right? Which is probably what most of us are most familiar with. It typically, not typically, but it needs to be a tabular deposit, moderately dipping, maybe even what you would consider steeply dipping. Okay, there are longwall mines in China that are operating on about 45-degree angles. Just typically used in coal, but also they run longwalls in China and potash. So, and theoretically, you could run it in a salt mine too. There wouldn't be a reason why you couldn't. Just people don't tend to do that. And I know my head is cutting off this slide, bottom of this slide, but you can think of caving methods as, so you create an opening underground and systematically allow the ore or the host rock to cave, right? This generally requires a relatively large reserve, especially like when you're looking at, longwall coal mining, right? You need to be able to keep the mine open long enough to make money, so you're looking at larger reserve areas. So, block caving. Here is an excellent diagram that I found on block caving. And basically, what you're doing is you mine underneath the ore body, and then you allow the entire ore body to cave down to the draw points. Okay, so you're caving the entire ore body, right? So you get massive amounts of subsidence. And this can show kind of what that looks like, right? As of about 5 years ago or so, these were and I'm cutting out anything that's in New Zealand or Eastern Australia with my head again. I wish I could move that thing, but I can't. That's okay. I'll just put the slides on the website as well. But here you've got the block caving mines in the world, except Bingham Canyon. Don't count that because they did decide to at least postpone, maybe even indefinitely, going underground. Here's the Resolution mine that's maybe started now. I'm not sure. I know it's in talks, but a project that was supposed to start here. You've got several of the big copper mines down in Chile, block caving, right? Diamond mines in South Africa, and maybe some of the gold too. I'm not 100% sure what all these mines are. And then some over in like Indonesia and that area in Asia and Australia. So I mean, they're on, almost every continent. I don't see any in Europe. Maybe there's some now that I don't. Maybe there's a new one or something that's been in the past few years. But anyways, widespread around the world, and a major method for producing our metals. This is an example of the Ridgeway cave zone. This is in Australia, from a block caving mine, and this was in as of 2004. I don't know what that looks like now, but you can see how massive the caving is here. Next up, we have sublevel caving, okay? And like I said, it's not all that different, except, once again, you're accessing the ore on sublevels, right? You would come in on level 1, mine it. Level 2, mine it. Level 3. And then you're breaking this down all the way down, right? And so you get this sort of caving that continues like this, and then it gets less and less, but it's very but it's still a high amount of subsidence. Okay, this is the Kiruna mine, LKAB's mine in Sweden. It's north of the Arctic Circle. It's a very large mine, and they've been mining ever since. And this is an iron ore mine. Okay, so it's not copper or gold, but it's iron ore. And this mine has been in production since 1898. It's 1900 right here at the top, level of 0. And now their current haulage way is down there on 1365 meters. That's right about 4,500 feet deep. Okay, and so what they're doing is, a lot of it's LHDs, load haul dumps that they're using to actually extract the ore, and then loading it. They'll take it over to a crusher and then send it out, in skips. And so it looks horizontal. That's because it is, right? The ore body's vertical, but they're accessing it from horizontal drifts, right? And then caving it from below. This is the actual picture of the town, and a friend of mine works here at this mine. He used to be a NIOSH researcher and was a former West Virginia University graduate. He married a girl from Finland, and moved over that way. But for whatever reason, they ended up in separate countries. So, but he's working at this mine up here in Sweden, and it's really a neat place. And except they've had to start moving the city center, and the reason for that is with mine expansion, the subsidence is problematic. So they're having to move the city center, which is kind of interesting. But yeah, they've been mining in this area, iron ore in this area for 125 years in this mine. And that takes us to Longwall mining, which is, like I said, what we're most familiar with. And for this, I have not the original. This is an electronic sort of rendition of the old Joy Mining sort of poster, right? We had these on our wall when I was a student. I even had one on my wall at NIOSH. It was, they're still out there. And it kind of shows everything involved in modern underground coal mining. Okay, you've got everything on the surface here, prep plants, silos, that sort of thing. A thermal dryer is labeled here. They're out there primarily used for metallurgical coal and certain specs where you need a thermal dryer to actually dry out the coal because of the moisture content. But they're not everywhere. And then of course it comes out and it goes all the way to the plant. But you come over here and then you finally have the top of the slope here, and you've got slope and belt going down. You've also got elevator for personnel and air. And then you've got rim and pillar, continuous miner sections that develop for the longwall, which you have shields across, and then longwall shear that's just taking out about a 3.5 foot, web of coal, across the face, back and forth, relatively continuously. Okay, so that's longwall. Here's a couple longwall mine photos. These are both taken out at Lila Canyon. In one case, they were getting ready to mine through a fault, and they had just gotten there in the tailgate. And so I'm actually standing on the fault in that left photo. My coworker's taking my photo, and his head's down around where my feet are, right? So there's about 6 feet of offset right there. And on the right side, this was the longwall face. So this mine, it dips pretty decently. It's about 10 degrees or so. It was about 12 feet thick, as you can see. Massive shields in this mine. 2,000 ton capacity. ZMJ. So these are Chinese shields, and they've got the front flippers because this is burst prone ground. So in case you have any burst from the face, that's helping out with that. The guys running the shear and stuff, they're all dressed in basically baseball catchers outfits or motocross padding and that sort of stuff. The longwall coordinator actually, after we finished up down there and before he left and went to another company, they'd actually been injured by a piece of coal off the face and actually punctured one of his lungs. So he had to go to the hospital and stuff. But anyways, this is a good example of a longwall mine that's maybe a little bit different than what we encounter around here. It's not all that different than right over at the Buchanan mine, other than the roof is a bit, the overburden's a bit stiffer here in Utah than it is here. And the mines are deeper, right? Because this seam's dipping at 10 degrees. It doesn't take long for you to get to beyond 2,000 feet of cover and pushing 3,000. Okay. Those shields out in Utah at Lila Canyon were basically, they were top coal caving shields, which you see in the photo here. These were invented by the Chinese, or invented in China. And what happens is, so if you have a really, really thick coal seam, you can't mine at all, right? And there's a couple of methods that you can use. You can mine in lifts. And so what they would do is they would longwall the top, and as they were mining, they would put mesh on the ground, right? And let the cave fall on top of it. So they would mesh the floor. And then they would just mine a big area, and then years later come back, and that rock be reconsolidated. It would mine underneath it again, and bolt up into the top and stuff. So they had mesh, and it would just combine itself kind of back together. They'd mine another lift and do it that way. And then eventually along came top coal caving, right? Where you basically just take the shield, make it a bit bigger, add this extra flippy gate on the back, right? So you've got an extra piece of shield, a gate that opens, a second AFC, right? So you've got a second armored face conveyor the coal breaks off, falls down, and you can recover probably, I don't know, at least half of this coal, up on top. And it all depends on the rock too, what the cave looks like, what percentage you can get out of here. But it's significant, right? And it's a lot more productive than doing doing it in lifts. There's another picture of a ZMJ shield. The tallest shields in the world are made in China. I'm sure this guy is not 6 feet tall, but he's more than 5. Okay, and you can tell by his scale, the size of these shields. These were 20 foot, basically 20 foot tall shields, right? And you got the shear right here. It's so big you can't even see the drums on it, right? So massive equipment for the massively thick coal seams over in China and in Australia as well. Yeah, so lots of shields being made in China. Even you can even get cat shields that are manufactured in China and brought back over. So this is very much a global sort of economy in mining, more so now than has ever been. Well, I shouldn't say ever, but I mean, there were also times when the Germans were making leaps and bounds in longwall technology, and so that's some pretty big equipment for some pretty thick coal seams. Finally, we also have a plow. And this ended up being a relatively terrible photo, but this is a Caterpillar plow. These were last used in, this came from an article about the Pinnacle 50 mine. So the last 2 plows in the United States were at that mine, which operated in Wyoming and McDowell counties primarily, and the Pocahontas number 3 seam. Which in that area, they had about 53 inches of coal or so, 50 some inches. So it's relatively thin. You had to crawl along the face. I remember that was the first coal mine that I ever went on a tour at when I was a student. So I got to see the plow face and that sort of thing. And it's all automated, right? So it's just running back and forth. It's taking a very thin web of coal, 6-8 inches or something, maybe a foot if the coal is pretty weak, because it's just scraping it off the face, but it's doing it at very high speed. So it's drug back and forth, just whittling coal off the face, right? And for thin seams is a very high production method, right? I think the record at Pinnacle 50, at least from that article, was in a 24-hour period, in 53 inches of coal, they mined out right about 35,000 raw tons. That's a lot. But for a plow, you really can't have any rock in the seam because if it's strung at all, the plow's not going to be able to break it. So these are very popular in Germany before they quit mining. And some of the thinner seams that they had, I have at least read of capabilities of German plows for mining seams as thin as 24 inches. So, longwall shears are also used in other commodities as well, just like with room and pillar mining. We've got longwalls operating in trona. We also have longwalls operating in potash. Okay, once again, you see here they've got the shear down on this end, changing out some bits. Vertical legs on these, I don't know when this was taken, but vertical legs on these shields, and then of course the tunnel boring machine with these curved ribs on the side. So this was a trona mine. I think there's 2 longwalls operating in trona right now. I think if I have that correct. Yeah, so there's multiple commodities, and like I said, theoretically you could use a longwall and salt, or something that says you can't, with the exception of consider the caving, because You know, all these salt domes are underwater. They're either out underneath Lake Erie or Gulf of Mexico. And then finally, I'm going to close it out with a photo that I found while I was looking through my other photos for this presentation. And this is my great grandfather. This is my mother's grandfather, and that's outside of the party and curtain number 4 mile in Webster County, West Virginia. So with that, if you have any questions, feel free to reach out to me, and we'll see what we can find out. So but thanks a lot, and we'll see you next time.